Hey everyone, I'm Ahmed from Ahmed University, and today I'm going to talk about big O notation. It's one of the topics I really love in computer science. Let me start off with an example. So let's say if I wanted to send a file from my device to a friend of mine across the country. So how I'm going to do that? So the first thing that comes to my mind is I will shoot him an email and attach the file into that email, or upload the file to an online service like Dropbox or Google Drive and send him the link to download it. What if the file size is too big? What if I wanted to send him a 5 terabytes? And sending the file will take 10 days or 20 days to upload the file and to download the file on his device. What is the other solutions? Then I will start thinking about, okay, how about I just export the file to a flash drive and take a flight to his city and just go deliver the flash physically. And this is going to take only, the time of the flight? 1 day. That's the second solution. What if the flight is not an option? What is the other solution? How about exporting the flash and drive all the way to his house and deliver the flash and the data physically? And this is probably just going to take 2 days. So how efficient are these solutions? So the first solution using electronic method will take O of n, where n here is the size of the file. The more the file size increases, the longest it's going to take to send it. And for both car and plane, it will take a constant time of 1 to send the file. So what we just did is calculating the efficiency of the solution using a mathematical way, which we called the big O notation. And that falls under asymptotic runtime. In order to understand what is asymptotic runtime, I'm going to explain 3 asymptotic runtimes, and we'll explain the difference between them. So first, we have big O notation, which calculate the worst growth rate for your solution or algorithm. And big omega calculate the best growth rate for your algorithm, and theta tries to calculate the exact growth rate. And I'm not sure if it can get it right. And if you look in the following graphs, in the middle, big O notation, the line above f of n, that's the worst growth rate for f of n, cg of n. On the right, cg of n below f of n, which is the best growth rate for f of n. And on the left, there's theta, where we have 2 points, one above and under f of n, and theta is trying to get it's think about it as it's the average between these 2 points. We are going to talk about the common big O orders. So these are the orders you will see in the following examples. Starting from left to right, O of n factorial, that's considered the worst running time ever. If your algorithm runs in n factorial, you should redesign your algorithm and try to enhance it as much as possible. O of c to the bar n, n to the bar c, the next worst solution running time complexity. These are exponential running times. O of n log n, it's not as bad as the exponential or factorial running time, but it's not the best solution. O of n, which is that linear running time complexity, it's fair. O of log n, logarithmic running time, it's pretty good. And we have the final running time O of 1, which is the best running time you could ever find if your algorithm or solution could be run in O of 1. That would be the best running time. So next, I wanted to talk about or mention this definition of something called amortized time. It's here we're looking for the worst case running time per operation. Operation could be adding an element to array list. Operation could be getting an element from a data structure. It's as simple as that. And amortized time or amortized analysis analyzes that operation and gives you an input whether you should be worried about that operation or not. And without further ado, let's jump right in to some examples. So before we started, I wanted you to pay attention to the left corner and the right corner. So there is an ask yourself, number of iterations of fastest growing term, and try to ignore any constant or coefficient when you are calculating the big O. Okay, for the current example, this is a simple calculate distance. We have for variables, and we are applying a mathematical expression. Okay, ask yourself number of iterations. We don't have any iterations. Fastest growing term. We don't have any fastest growing term. It's a static operation. It's basically a static function with no variables, so it's O of 1. You know, remember the plane? This is a plane solution. It doesn't matter the size of the variable because we don't have a variable at all. Next, hello, big O. Same thing, no iterations, no fastest growing term, O of 1. Boom. Next, multiply numbers, same thing, no number of iterations, fastest growing term, O of 1, time complexity. Next, reverse array. Okay, we have a parameter, a variable, array. We're going over array over 2. So the number of iterations is going to be n over 2, which means half multiplied by n. We said, okay, number of iterations, n over 2, ignore constants, half multiplied by n. So it's going to be O of n. All right. Next is prime, number of iterations. We ignore the if statement. We goes from I equals 3 to square root of n. Number of iterations is going to be square root of n. So the big O notation will be square root of n. Next, factorial, number of iterations. Ignore the definition long fact equal 1. Go right into the for loop from 2 to n. Number of iterations, n, complexity of n. Next, Fibonacci using matrix. You just go right into the iteration. Number of iterations we have from 2 to n minus 1. Iteration is going to be n, so your time is O n. Next, Fibonacci dB. Ignore all the definitions. Go right into the iterations. We have what? From 2 to n. So number of iterations is n. Complexity will be O of n. Same thing. Go right into the for loop from 2 to n. So iterations n. Fastest growing term n. So it's O n. Adding elements to array list. The same thing as before. It's an O n problem. But here we only have an array list and we are adding elements to array list. So do you remember the amortized time, which is concerned about calculating the worst case per operation? Here we're talking about the addition operation, adding an element to array list operation. There is a worst case. When you reach the capacity for the array list will have to resize the internal array and copy all the elements over to the new array. That's an internal implementation for array list. But they told us do not worry about that operation because once the worst case happened, it will never happen again. Next, here, number of iterations. We have 2 for loops. Okay, what? I'm hearing someone say, okay, let's O of n square. Oh no, holy horses. Do we have variable here? Do we have any variable? No, we don't have a variable here. So it's O1, it's constant. Next, we have a parameter, a variable, array, and we're going over the array twice. So we have O of n square and multiplied by n iteration. Next, same thing, but here we have 2 arrays, and we're going over the first array, and we're going over the other array. I'm hearing someone saying O of n squared. No. Like when you say n squared, this means what is n? N multiplied by n. So here we have, we need a variable like the length of array 1 and the length of array 2. So it should be a multiplied by b, not n squared. It's not the same array. It's different arrays. Next, we have an array. We're going over the array twice, but in the second time, we're just going over half the array. It's the same thing. It's as if we're going over half a 2-dimensional array. And as we said, ignore the constant. So it's going to be O of n squared, as if half n squared. Ignore the half, and it's going to be O of n squared. Balanced binary search tree. I'm assuming everyone knows the binary search tree and how to search a binary search tree. Here, in any problem, in any function where your problem is cutting into half or cutting into a constant type, either it's 1 over 2, 1 over 3, 1 over 4, your problem is decreased by half every iteration. This is a logarithmic operation. It's a logarithmic operation. Go for logn immediately. So next, We have here, same thing. We have power of 2 every time. We're calling the same method with n over 2. What n over 2 means? We're cutting down the problem by half. So with any function, you're cutting the problem into half. 1 over 2, we're cutting problem 1 over 3. When cutting 1 over 4, your problem is cutting into constant variable. This is a logarithmic operation. Same thing here with the square root of x. You start from 0 to x and you try to get to uh, the square root of x. So you're cutting your timeline into half. Get the middle, compare the middle, whether should I go right or left, and then go to whether you went to right or left. You will end up splitting your problem into half again. So still, that's a logarithmic operation. It's all log n. Next. So for this example, in Fibonacci, this is the opposite of logarithmic operation. You have a call, Fibonacci, and you have two calls in it. So your problem is increasing by a constant factor. We mentioned before in the previous examples, when your problem is cutting down into by constant, you're cutting your problem down by constant. This is a logarithmic operation. But when you're increasing, your problem is increased. You're making more calls by a constant variable. This is an exponential operation. So in this example, it will be 2 to the power n, which means the problem is increasing every time by 2, as if you're multiplying by 2 every time. So the time is all 2 to the power n. Next, and in this example, it's permutation, number of iterations here, which is going to be like a recursive calls. It's similar to the exponential example that we just mentioned, but with slight difference. So here, back there, every time our problem is increased by 2. So every time Fibonacci, we call n minus 1 and n minus 2. The problem is increased by 2. But here, the problem every time the problem is increased by n minus 1. So if you look at the image on the right, so you would found the first call, I am doing 3 calls, A, B, C. And in each call, in A, for example, I am doing 2 calls, B, C. And in the next call, I am doing only 1 call. So this is what we call like a factorial running time. So thank you everyone for sticking around. Please leave me a comment if you have any question. I'll see you in the next video. Thanks. Bye.